Okay, so welcome everyone. I want to thank you for joining us and welcome to today's webinar. In lieu of this year's in-person best practices exchange, Efficiency Vermont is pleased to present this three-part webinar series to highlight critical energy efficiency technologies for businesses. These webinars provide expert guidance on lighting, variable frequency drives, and HVAC controls, with sessions presented once every week for 3 weeks. And today is actually our second session with the topic of lower your operating costs with variable frequency drives. And pleased to have as our presenter today, Chuck Clarici of Efficiency Vermont. If you have any questions throughout the presentation, please just use the Zoom Q&A tool. You should find that on your screen. So you can send in a question anytime. We'll monitor that, and Chuck, he'll be happy to answer you throughout the presentation. And then lastly, again, this session will be recorded. We'll post it to efficiencyvermont.com for later viewing. So with that, again, welcome. And Chuck, the floor is yours. I'm going to go on mute and stop my video.
John, thank you very much, and good afternoon, everyone. Thank you for taking time out of your busy day on your lunch hour to join us to hear me talk about variable frequency drives and how they are a great technology for lowering your operating costs at your customer facilities. We'll be predominantly talking about pump and fan applications today. I can't see the audience. I did look at the attendees beforehand. I see quite a few people who are concerned with HVAC. That is where we see about 80% of our VFD business. The other 20% is in process manufacturing primarily. Most of today's conversation will be around HVAC, but if you do have process related questions in manufacturing, feel free to put those in the chat and John will get those to me. John and I have a tale of two seasons backgrounds going on. It's heating season now. Heating systems are firing up. You're in boiler room, some of you, making sure that the systems are running in advance of the snow flying here and the cold weather coming in. So it's a good time to look around the HVAC operations and see where things can be improved from an energy standpoint. VFDs are an interesting add-on. They don't fix what's broken. Moreover, there's just simply speed controllers that allow us to slow down pumps and fans and secure energy savings. So I get really excited about VFDs. I've been working on these for 6 or 7 years here. Had a lot of success in my customer base. I get really excited about them, kind of like all the kids this week before Halloween and all the candy coming. So with that, John, I'll ask you to advance the next slide, please. So why VFDs? Why now? VFDs save energy. They reduce wear and tear. HVAC is a pretty significant load in most commercial buildings. This really looks at non-manufacturing buildings. There is, of course, HVAC in manufacturing plants, but a lot of the heat is usually derived from process. So this metric here in the upper right is looking at your typical non-manufacturing building. Roughly 38% of building energy is consumed by HVAC. And if you break that down further, with the graphic in the lower right, you'll see, combined 19% of that, or about a fifth of the overall building energy is consumed by pumps and fans. And that's kind of the target for our VFDs. We're looking for things that take advantage of the affinity laws. So when you slow a fan or a pump down, a centrifugal load like a pump or fan, you get cubic savings. What that means is if you slow a fan down 10%, you will get about 25% energy savings. So it's better than a linear relationship, which is why VFDs are so cool. If you trim off a few hertz from the top end of a pump or a fan, you can pick up cubic savings, and that's really valuable to Efficiency Vermont as well as to the grid. One of the other reasons we are so excited about motor controls. Motors account for 69% of industrial power consumption, 45% of global power consumption. Motors are everywhere. In a typical manufacturing building, 80% or more of the connected load in the facility is typically motors. These are pumps, fans, compressors, refrigeration compressors, you name it. There's motors in every building. We also have lots of motors in our homes and in our commercial businesses. If you've worked with Efficiency Vermont over the past 20 years, you know we have very mature lighting programs. We've been in the lighting business for a very long time, and with the advent of LED and the adoption of that over the last decade, we're really squeezing the last juice out of the lighting market. But by comparison, lighting is a very distant second to HVAC. It's right now it's about 19% of typical building energy use, HVAC being twice that. And if you look specifically at Vermont, it can be even above that because of the number of heating degree days that we have here. Next slide, please. So some of the basics, as I mentioned earlier, a VFD is simply a motor speed controller. Absent a drive, a motor can only run at one speed, which is 60 hertz. It loads and unloads based on the demand on the motor. If it's a fan in a fixed volume system, it's going to have kind of a constant load on it. Same goes for a pump. But the point is, absent a drive, it can only run at 60 hertz. And with the drive, it can modulate lower than 60 hertz. And in some cases, it can modulate higher as well. Some synonymously used terms, VFD, VSD, ASD, they all mean the same thing. They simply change the shaft speed of a motor. They do require an input signal. There are some drives that can be done what's called set it and forget it, where you just turn it down to a fixed hertz speed. We have some pumps like that in the brew industry in Vermont, where the pump is a bit oversized, and so it's turned down to the point where they need the fixed flow, and it's left there. But that's a rare exception. In 99% of the cases, we are asking the drive to control the motor by way of pressure, flow, temperature. Those are probably the prevailing ones in HVAC, certainly. If there's not any questions, we'll move to the next slide. Control signal, simply putting a VFD on the wall doesn't save energy. It's got to be installed correctly. It's got to be started up correctly. It's very similar to the programmable thermostat in your home, be that a 5.2 thermostat or a Wi-Fi thermostat. It's as good as the settings. And periodically, it's good to go back and check those settings. We at Efficiency Vermont will be talking internally about doing periodic recommissioning just to make sure that the drive settings are correct and that the intended savings is preserved. There's a couple communication options typically with drives. There is a variety of drives out there, just like vehicles, there's sort of low, medium, high-end cars, just like there are drives. There's a lot of different communication, BACnet, Modbus, Lawnmark, a bunch of other ways of communicating from the drive back to a BMS or a SCADA system. Next slide, please. So here's some basics. Rule of thumb for HVAC VFD is about $200 per horsepower annual savings potential. This is going to vary, of course, but if you're out in the field or you're in your boiler room or your facility and you're looking at motors, on pumps and fans, and you're wondering, is this motor or is this fan or pump worth controlling? $200 a horsepower is a starting point. We can refine that through analysis. We have a lot of tools at our disposal here at Efficiency Vermont. We do a lot of power logging on larger motors, typically probably at least 5 horse and above. The smaller horsepower stuff, we usually just estimate on paper. Lifetime savings over 15 years for these typical measures. So this is a 5, 10, and a 25 horse example. Lifetime savings over 15 years, which is the typical measure life for a VFD. For 5 horse, you can see is $17,000 and change. 10 horse is $33,000 and change. 25 horse is $82,000 and change. these projects, as you'll see in a few more slides, almost always have a 2-year or better payback associated with them, with rare exceptions. If you're specifically talking HVAC pumps and fans, it's almost always in that 2-year or less, sometimes down to even a few months. And we have some case studies I can show you later on that point to what great projects these are for us, for the customers. Customers are always looking for rapid payback projects, and VFDs really deliver on that. If there's no questions, we'll move on to the next slide. HVAC application. So we have 7 prevailing applications. You can see them listed here: air handler, supply and return fans, exhaust fans, ventilation units, cooling tower fans. Then on the pump side, circulator pumps, chill water pumps, and cooling tower loop pumps. These are 7 of the most prevalent pump and fan applications in HVAC. Because there are so many data points on these, both in Vermont and nationally, we have an agreement with the Department of Public Service that by horsepower, by VFD application for these 7 applications, we have what's called ascribed savings. So if you have a 10 horse supply fan and you put a VFD on it, it equals X amount of savings, and we can do our project analysis based on that. So this is the target audience for HVAC. There are applications in HVAC that are outside these 7, and we encourage you to bring those to us and have a conversation. This is not to say that these 7 are the only homes for VFDs, but these are the prevailing ones. So we've kind of built a program around it. On a custom basis, we will handle drives on all different types of applications. We have conversations daily about various applications for VFDs, where we've had a bunch of conversations recently about irrigation systems at golf courses and water supply systems. And the short answer is, sometimes they're a fit and sometimes they're not. But even when they're not, we generally end up having good conversations about control strategies for these different systems. So there's something to be had in the conversation, even if it doesn't result in confirmation that it's a good drive application. No questions, we'll move on.
That's correct. Yep. And just chiming in here, this is John. So folks, you can use the Q&A tool on Zoom if you do have questions, and Chuck doing a great job.
Thanks, John. Okay, so some more on HVAC applications. I walk through boiler rooms all the time, and I walk through customer facilities all the time, probably 3 times a week, all year long. I came from a mechanical contracting background. My dad and brother are both in the business. I've been in boiler rooms since I was a little boy. So I know my way around, and it's more common than not that I walk through a boiler room and see circulator pumps. If I go up into the building, air handling units, exhaust fans, all absent VFDs. We're probably looking at maybe 10 or possibly 20% market penetration in terms of drives on all of the pumps and fans that could benefit from VFDs. And that's what's gotten Efficiency Vermont really excited. And of course, we're putting our money, the ratepayer money, where our mouth is. We have a very generous and aggressive program to support drives. That is by design. If we look around New England, Metro New York and Metro Boston, the adoption is quite a bit higher in those markets for VFDs. So, we want to catch up, and we want to make sure that we are deploying these, with a lot of caution, make sure that they're properly, the application is properly thought through, the control schema is thought through, and that we want to secure the energy savings so that we can, help you as contractors or help you as building owners convince your financial decision makers that these are good investments and gain their investment. Benefits of load matching, we're in the energy savings business, so that's our driver here. But there's other benefits to using drives. When you've probably all been in a room where there's excess airflow, and at any given temperature, excess airflow is going to make the room feel cooler, sometimes too cool. And that's probably because the air handler or the rooftop unit only has a single fan speed, so it's blowing constant. And if it's not matched properly to the space and wasn't balanced properly with dampers, it's going to blow excess air. If you're holding back fans with dampers, you're making that fan work harder just to do a part load job. That's where the VFD can really shine. Slow the fan down, you can open the damper back up, you take a lot of load off that fan and you save a bunch of energy. Of course, reduced motor speed equals reduced heat. That gives life back to the equipment. And VFDs are an excellent soft starter. They are a better soft starter than a soft starter. Which is why, the utilities on larger motors like snowmaking pumps require drives for the soft start capacity on big snowmaking pumps. But that same principle applies to a 10-horse supply fan. It's very different when you slowly ramp up a motor versus banging it across the line. You'll go through less contactors. You give some life back to the equipment, whatever that may be, an air handler, a rooftop unit, a pump. So multiple saving streams. This is probably most prevalent in sort of exhaust fans. So I do a lot of work in the ski industry. There's a lot of big kitchen hoods, 20, 30, 40 foot long kitchen hoods with lots of equipment under them. The hoods are sized for everything under that hood to run simultaneously, and that's rarely a case, especially midweek at a ski area. They're making a few burgers for the midweek staff, but the fan's got 1 or 2 speeds. Most of the time it has 1 speed, so it's on full tilt. The fan energy is about 5% of the overall energy consumed. 95% of it is the rejected heat out of the building. Which then your boiler or furnace or other heating system has to make up for. So sometimes it's about electric savings, and in the case of exhaust fans, it's really more about the BTU savings. And if it's a cooled space, you'll get some derivative kilowatt hour savings from reduced cooling rejection as well. As I said earlier, these paybacks are rapid. We have customers often saying, give me something in the 1 to 3 year range. That's kind of the sweet spot for energy efficiency projects. Drives are beautiful in that they fit very nicely, in the 2 year or less. And with our rebates, we can often get them down to, a year, maybe sometimes even better. All right, if there's no questions, we'll move on, keep rolling here. Talked about cost-effective energy savings. We can do 400 light retrofit project, or we can put a 40 horse VFD in and secure about the same amount of savings for, a single line item transaction. So the sales cycles can be shorter, the implementation cycles can be shorter. Especially when you're dealing in the HVAC realm, you're dealing with mostly 50 horse and under drives. Those are predominantly off the shelf drives in normal times. This market has been hit by the supply chain issues, just like everything else. There's plenty of electronics and chips in these boxes. So we've experienced some delays in the supply chain. But there is still product out there. We're told, we check with our supply chain partners all the time. Last check, there were over 50 OEMs of VFDs. And so there's certainly still supply. Most of the drives that we see in Vermont are, in fact, probably 30 horse and lower, with the average drive on an HVAC application probably being around in the 10 horsepower range. We have great rebates. I'm going to get to that in a minute. Just a note, this footnote here, VFDs that are required by the Vermont Commercial Business Energy Standard are not eligible for rebates. This would be new construction. So we have a pretty robust and modern energy code here in Vermont. It does require VFDs on certain applications in HVAC and refrigeration. If it is required by code, we do not rebate it. But if it's a retrofit application and it's a good fit for VFD, we will certainly extend an incentive to that project. Okay.
Hey, Chuck.
I think I see a question.
Yeah, you want me to read it for you, or are you able to see it?
I can't see it, so
Okay.
if you wouldn't mind reading it to me, please.
Sure. Bob asks, do you if you want to give rebates if you're switching from soft starts to VFD? And then there's continued part of the question. We want to replace 125 horsepower motors to take care of inrush current. And then he says he works with Dave Adams at Efficient Vermont, and he hasn't asked him this yet. So Chuck, do you have any thoughts?
Potentially, yes. I need to know the application. So as I said earlier, the VFD will do a much better job than the soft starter in handling inrush. Inrush is a very short duration event, but it's an important event especially if you're a utility company. Across the line starts can cause brownouts or worse. The question in terms of do we extend an incentive has to do with whether or not the load can be modulated. So I didn't hear in that question what the 124 horse was tied to. If it's a pump or fan that can be slowed down by way of a signal, power pressure flow typically, then potentially, yes, we can extend an incentive. If the drive is simply for soft starting, we cannot.
It's for a sewer pump, just to chime in with his response. And I would say, Bob, definitely connect with Dave Adams directly, but Chuck, it's for a sewer pump, if that may change your answer.
Bob, there's a pretty good chance that the answer is yes. Unless we're talking about the 7 HVAC applications, I'd never say 100% yes until we get a little bit more detail. But I want to have these conversations. So thank you for bringing that question to us. And please feel free to bring it to Dave Adams, and you can copy me as well if you like. We will get one of our energy consultants to take a look at it. We have a team of people who are sort of specialized on wastewater treatment operations. So we'd route it to them. Thanks for the question. Gonna go to the next slide, please. Okay, so here's a bypass system. You'll see a throttling valve and a three-way valve. This could be water, it could be air. It doesn't really matter. We have bypass systems and throttling valves on both type of systems. When you're throttling a pump or a fan back, that pump or fan is still running at 60 Hertz. It still has, a single speed that it can operate at. You're just sort of choking it back, and that's not inherently efficient. You're making that motor do more work than it has to. So when you put in a VFD on a pump or a fan, you can eliminate the throttling valve and the three-way valve because you can simply slow the VFD down to deliver to match the demand, whether it's heat, cool, air, exhaust, whatever it may be, whatever the demand is. We just simply slow the motor down. This is not dissimilar to thinking about, driving your car with just the brake. If you started your car up and it went to full RPM and you just used the brake to go and stop, that's kind of what this diagram is absent of VFD. So the VFD just sort of gives it the accelerator so that you can, match speed to how fast you need to go with your pump or fan. Next slide, please. Identifying the opportunities. So some of the questions that we ask our customers when we are endeavoring to look for VFD opportunities, talk to me about the single speed motors in your building. And you may get deer in the headlights look and have to explain exactly what you're looking for. And really what you're trying to find out is, do they control their motors? Is there an active effort, or has there been an active effort at your customer or at your plant? I realize we have contractors and customers on the line, to control your motors, because if you haven't, then there's probably abundant opportunity in the building to look at different motors for the application of VFD. And then another question is simply, corollary to that, do you have any motors in your building or pumps or fans in your building that you think could be slowed down? And we get all kinds of answers. We get, there's no snow on that side of the building because we exhaust so much heat over there. Or it's really cold in the kitchen, during the week at a ski area because we're exhausting so much heat out of there. Or, it's really cold in the conference room because there's so much airflow in there. Those are some, key indicators that you're overdriving a pump or a fan, and there's an opportunity there to slow it down vis-a-vis a VFD. We target high horsepower hours, and what I mean is, I'd rather go after a 5 horsepower motor that runs 5,000 or 6,000 hours a year than I would a 100 horsepower motor that runs 5 hours a year. Hours are everything. You can save a lot of energy, but you're only saving it in the hours that the thing runs. So, don't waste your time, hunting down very sparsely used pumps and fans. Go for the heart of the HVAC system, the bigger pumps and fans. When I walk into a boiler room, I'm inventorying all the circulator pumps in there, mostly in terms of horsepower, so that I can get kind of an overall horsepower for the pumping system. And then, depending on what else is in the system, air handlers or rooftop units, what have you, add up the horsepower on that stuff as well. And that kind of gives me an indication of how much opportunity I have in any given plant. And I want to remind you, I've reminded you a couple times here, but I will do it several more times. Partner with Efficiency Vermont. We're here for you. We're going to do this presentation many times over. We have done it several times over already. We have a bench of engineers that have various expertise in HVAC, controls, wastewater, industrial process. We've looked at VFDs on just about every application there is. Some of them are very straightforward, and we can give you a thumbs up yes, we can give you a rebate on that. Or some of them require a little bit more conversation. And if it's a really complicated or one application that is in question, we may just submeter. We'll put a power logger on the existing motor and we'll get a profile on it for 2 weeks. And then we'll sort of map out what we think we can look at in terms of turn down with the drive, and that'll sort of forecast the energy savings. We marry that up with the cost of the project and the rebate, and we get a payback scenario for the owner. And in many cases, it's nothing but green lights on these. So next slide, please. Yeah, you can load all these up, John. Thanks. Example VFD opportunities: constant speed AC motor driving a constant speed centrifugal device, pumps and fans, we've said it. The load is variable, outdoor air temperature, but the air or water flow is constant. System spends a large percentage of time at part load, which is pretty much by definition all HVAC equipment. HVAC equipment is sized for design days, hottest day of the summer, coldest day of the winter. That is, 10, maybe 20% of the hours in a year. So the rest of the year that we're heating and cooling, your systems are running at part load. And if your fans and pumps can only run at 60 Hertz, that's all you can deliver. You have no speed control to match pump and fan speed to the demands on the building. And that's where the VFDs really shine. The device is controlled by one of the following: inlet or outlet throttling, bypass loop, or no control period, which is the most common situation that we see. Most circ pumps out there, they're on off. Most supply fans on off. At most, they're 2-speed. 2-speed can diminish savings if the control sequences are set properly, because you're essentially running the fan at a slower speed. We have a couple kitchen hoods that run at 2 speeds, and if the operators are diligent about running at the lower speed, they are observing some of the savings already. They're not getting the throttling or the modulating in between the high speed and low speed, but they are securing some of the savings. So those are some of the types of questions that we ask when we go into a project like that, because to the extent possible, we're trying to be very accurate with our savings forecasts. Our customers come to believe in the savings that we do forecast. They invest in projects accordingly. So, you know, we need to keep a high standard around that. Next slide, please. Just more on the opportunities. You know, you walk into a lot of different stuff every day. As one of my mechanical contractor friends says all the time, you know, is the juice worth the squeeze? That's the question we're asking ourselves all the time. You know, that's a half horsepower fractional horsepower pump. Yeah, I could put a VFD on it, but it's only going to save $10 a year. Moving on. So we look for a high horsepower first, whether it's in HVAC, whether it's in a water system, a wastewater system, process manufacturing. Start with your highest horsepower. Run through the series of questions. Is this a centrifugal load? Can it be slowed down? If the answers are yes, proceed. If the answers are no, move on to the next lower horsepower. We're looking for stuff that has run hours in 2,000 hours a year and above. There are 8,760 hours in a year, non-leap year. So 2,000 hours is, you know, roughly 25% of the time, a little less than 25% of the time and more. Most of your HVAC equipment is going to run in the 2,000 to 5,000 hours a year range. So again, that's just sort of underscoring that those pumps and fans are kind of the sweet spot for VFDs. Centrifugal loads, applications where fan or pump speed will modulate based on differential temperature or pressure. That's typically your two signals. Flow would be the other one. A drive can be controlled by multiple signals, but in most HVAC applications, it's usually temperature or pressure. And occasionally flow. Existing systems include throttle or bypass. Throttle and bypass is like it's a big red flag, but also a green flag in terms of opportunity. If we see throttling and bypass valves, you know, that's usually a really good indication that there's a VFD opportunity there. All right, next slide. So here's a little example. Cooling towers are just a home run. If it's not a modern cooling tower, and I mean one put in the last 5 years that's been subject to energy code and probably has VFDs on every pump and fan, you'll run into a lot of cooling towers that don't have drives on any of the pumps and fans. So there's, you know, pumps that move water out and back from the cooling tower. There may be additional set of pumps that move it to a cooling well or clear well. There's a bunch of fans. Sometimes there's spray pumps. So there's a lot of pump and fan loads connected to a cooling tower, whether it's for process or in this example, it's for a water source heat pump loop in a hotel. Putting drives on all of those pumps and fans can be extremely impactful, as is evidenced in this example. This is 830,000 kilowatt hours per year. Our rebate was just a paltry $15,000 on this project, and it got it to less than 1 year payback. Really great project. If you are working on cooling towers or you have a cooling tower in your operation, please reach out to us. We'd love to talk to you about you know, pressing some more drives in there, where they fit, where they make sense. And if you need help getting connected with a contractor, we have a great network of energy efficiency network partners that are qualified to work on VFDs as well as supply chain partners. So if there's no questions, let's move on to the next slide. So as much as I'd love to get drives on everything, it's not practical, and there are some caution signs to look out for when you're out there looking at VFD opportunities. So high static head pump loads, this is some water systems, non-centrifugal pumps and fans, so positive displacement pumps, for example, not a great application for a VFD. Loads with 2-speed motors. I talked about this in the context of the kitchen hood fans. It's not a no-go per se. It's just a moment to pause and maybe ask a couple extra questions. If we're really in doubt, let's log the motor with a power logger and see if we can get some more intelligence on how much energy it's consuming in the baseline condition, and then how much more we could slow it down while still meeting demand with a VFD. Loads with existing mechanical speed controllers, non-inverter duty rated motors. This is an important one. VFDs are also referred to as inverters. In order for a VFD to work, the insulation class on the motor has to be inverter duty rated. If it's not, you risk burning up the motor. So in that, again, this doesn't necessarily mean that's a no-go scenario. It just means that project might morph into a motor and drive project as opposed to just a drive project. And if the motor type is unknown, we've all seen motors out there in the field where the nameplate is completely rubbed bare. It's so old, it's hard to know exactly what type it is. You'd certainly want to proceed with caution, putting any drive or really any control device on that motor. A failed VFD. So for quite some time, our signal to the market was, we will not support replacement drives. There's been some movement on that front. It's not a slam dunk. We have some questions to ask. They are predominantly around whether or not the customer has to put a replacement drive in. If there's an energy code requirement, or there is just functionally no other way that this motor load is going to operate absent a drive, then we may take a pass on providing support for the drive. But there are quite a few examples out there where there are loads on drives, the drive fails, the motor can still run across the line. It may run in an inefficient state, but it will function and it will operate and it will do its job. If that is the case, then in those scenarios, it's likely that we will be able to support a drive. Facility is sensitive to resonant frequencies. So this is an electronic device. It creates harmonics. There are filtering devices that can limit that. If that's important to your customer, your facility, I encourage you to speak with your VFD supplier about harmonics and what they can do to mitigate that. Do that up front so that you're not surprised by it after, when the drive goes in, that it's actually part of the implementation process. VFD locations, not ideal. You need a clean and a cool space for these. They can be put in outdoor enclosures as long as they're properly rated for outdoor conditions. But we don't want them in very hot boiler rooms. And we don't want them in very dusty, dirty environments because they require cooling in the cabinets. There's fans that draw air across the electronics. If that gets plugged up, you have a heat buildup, and the drives don't like that, just like any piece of electronics. Facility has poor power quality. This can create problems, drives tripping and so forth. That's usually a problem that creates other problems for a customer. So they may want to fix that before they entertain looking at drives. Request to set a totally enclosed fan cooled motor to a low speed. There is a certain minimum speed for certain motors that has to be maintained for cooling purposes. So those are motors that you wouldn't necessarily want to run at 10 hertz because the heat buildup would be detrimental to the motor. So just another moment to pause and question which type of motor you have. Request to set the, I don't know why that says VRF. You have to fix that, John. VFD to overdrive 60 hertz. This isn't a deal breaker. I have customers who run dust collector fans over 60 hertz for clean out mode. A drive will allow you to do that. That's the only way you can do it, really. It's only for a period of time, short duration of time to clean out the ducts. The rest of the time, the system modulates and does what a drive is supposed to do, which is deliver energy savings by way of shaft speed modulation. So Just some words of caution. They're not deal breakers, most of them anyway. And if you run into these, please just, give us a call, drop us an email and say, hey, Chuck, or, I've got this application. I'm not sure if a drive fits here or not, but wanted you to weigh in on this. We get those emails and calls every day, and we're happy to take them. Next slide, please. So we have a standard rebate process for most applications, and for the 7 HVAC applications, it's very clear cut. These are 3 to 100 horse. You almost never see a HVAC motor above 100 horse, certainly not in Vermont. Supply fans, return fans, boiler draft fans, water source heat pump, circulation pumps, cooling tower fans, chilled water, and hot water heat pumps. Heating hot water pumps, I'm sorry. These are the end use applications where there's a clear lane to a rebate. The rebate is $150 to $200 a horsepower. For 2 to 5 horsepower, it is $200 a horsepower, and then above 5 horsepower, it's $150 a horsepower. If any of you have purchased VFDs, you will note, or if you're doing the back of the envelope math, that we come pretty close, if not entirely pay for VFDs. Certainly as the horsepower climbs and the price per horsepower of drives falls, the $150 a horsepower is very compelling. That is by design. We don't quite market it this way, but I will say it, we are in the business of paying for drives, where they fit, where they make sense. The customer then is on the hook for the installation and the startup. Some of those projects work out to be 50-50 sort of cost share between us and the customer. Some deviate from that, but at the end of the day, the paybacks here are often, 2 years or less, sometimes 1 year and less. This third bullet, VFDs must be new and cannot replace existing VFDs. I really kind of should put a ring fence around this, because I said before, I still would like folks to bring these to us. If there is a case to be made that, yes, I can run this across the line, there's no code requirement or otherwise requirement that says I have to replace the VFD, then I think we have a good case to extend an incentive and help you get into a replacement VFD. They need to be controlled by an automatic signal, pressure, flow, temperature. I gave you that rare example in a brew house where a pump is oversized, but it delivers a fixed flow of beer or wort. That can be a set it and forget it. We can do that on a custom basis, but for most HVAC applications, we're going to see control by differential pressure, flow, or temperature. And then, you can read the last note here: forward curve vanes, with inlet guide vanes, variable pitch vane, axial fans, circ pumps with integrated VFDs. We have a separate program for that. That's through the upstream at point of sale, and anything required by by energy code. Any drives required by energy code are not going to be eligible for incentive. So I will stop there. I see we have one question. John, if you wouldn't mind reading that, I'll take a crack at it.
Well, it's actually a question looking for your digital autograph. Adam wanted your email. I provided it. So actually anyone on the call can take a look at that to get Chuck's email and contact him directly. So that one's been answered, Chuck, but you got some fans out there. Great, thanks. Yeah, and my information's on the last slide, which I think we're very close to. Give you guys a few minutes back, eat your lunch. We can move on to the next slide. Eligible equipment, this is just kind of a rinse and repeat. The one noteworthy thing here is this is right from our website. If you have, or your customer has, a VFD on one of these applications on the left side here, they can create an online account on efficiencyvermont.com. They can file their application online and upload their invoice with the VFD model number on it, and we will rebate them in the mail up to $15,000 cash back. That would correlate to 100 horsepower HVAC VFD on a pumper fan. And like I said, there's not many. I don't think I've ever seen 100 horsepower
HVAC pump or fan in Vermont, but maybe they exist. Point being is this is an easy process. If you put a drive in on a qualified end use application, one of these applications on the left side, it is literally an electronic process, not dissimilar from getting a rebate from lots of different things. Upload your invoice as long as it clearly states the VFD model number on there and manufacturer, as well as the end use, which is part of the application. It's a very easy process. Non-qualified applications, failed VFD, I put the bubble in here, call efficiency Vermont. If we can make the case, legitimate case that this pumper fan could run across the line, the drive has failed. I had a compressor not long ago that had a drive on it. That compressor VFD failed. Now the compressor runs across the line. And it's been like that for 3 months. So that project, there's no code requirement or process requirement that says that replacement drive has to go in, so that the lane is clear to help support the replacement drive in that application. The question came up earlier about soft starts. If you're looking to replace a soft start with a drive purely for soft start capability, that's a no-go zone for us. VFDs for intentionally oversized motors, that's kind of a funny one because most HVAC motors are intentionally oversized. They are sized for design days plus 20% or so. So they are by nature bigger than they need to be for 85% of the days in the year. So put a little asterisk next to that one. We may still be able to help there. Backup pumps and fans, this is a good one because some customers have redundancy in their system. We are not in the business of putting drives on redundant pumps and fans that run only as fail safes. The drive doesn't save any energy sitting there waiting for another pump or fan to fail. So we're not going to support those. And I've said it several times. Anything required by energy code is not going to be eligible for rebate. So next slide, please. Here it is in chart form. This is all off our website. I believe it's also on our VFD informational sheet, which I'll pull up at the end here. These are your 7 HVAC end-use applications. You'll see the cooling tower fans and boiler draft fans are tapped out at 10 horse. There aren't too many boiler draft fans over 10 horse in Vermont that I've seen, but maybe there's a few. These would just be handled custom. I don't know why we have the cap on that at 10. It doesn't mean we won't handle above 10. It just means you'll have to bring it to us and we'll handle it on a custom savings basis. And then you'll see the 2 different rebate per horsepower amounts. Basically, the smaller the drive, the more expensive the drive on a per horsepower basis, dollar per horsepower basis. As the drives climb in size, they get cheaper on a per horsepower basis. So we have the 150 for everything 7.5 horse and above, and 200 for 2 to 5 horse. Below 2 horse, unless the thing runs around the clock, I'm not sure the juice is worth the squeeze. But if you think it is, give us a call and we'll talk it through. Next slide, please. That's it. That's all I got. John, if you want to stop screen sharing, I will pull up our VFD informational sheet. This is on our web. We can also send it to you. It is a leave behind piece that we send to customers. We give to mechanical contractors, facility owners. It just talks up the attributes of VFD. Motor speeds that can be reduced by 50% can save up to 75%. This gets at that sort of cubic relationship. When you slow a motor fan down 10%, you don't get 10% of energy savings, you get 25%, which is why this technology is so cool. We've got a small example here on a 10 horse rooftop supply fan. A drive on that saves about 6,000 kilowatt hours a year, $915. I was just talking with John before this call. I think we're going to update this with a little bit meatier example. We've got a lot of bigger horsepower stuff out there that is more indicative of the energy savings potential. Not that people wouldn't get excited about $915 a year in savings, but drives Huck a lot more savings than that. And if we scroll down here, you'll see some of what was just on the last slide, you know, the rebate per horsepower. And then on page 2, there are 3 real life examples. These are projects over the last few years that Efficiency Vermont's completed. This first example is a cooling tower project. It was about a $65,000 project, got a $13,000 incentive. Estimated first year savings was $86,000. So it's a 0.6 year payback and an 11-year measure life, 166% return rate of return on investment. Second example is a rooftop unit. This was a 0.2 year payback project. These are all on supply fans. And then finally, the kitchen hood, I alluded to this earlier. You'll see that there are really 2 saving streams here. There's a kilowatt hour saving stream, and then really, more importantly, a fuel oil or gas or whatever your heating source is, your heating fuel is. That's the big savings on a kitchen hood, which is indicative of really any exhaust fan. If you're over exhausting conditioned space, you're throwing away heating and or cooling energy excessively. If you need that level of exhaust, then you need it. But if you don't, and the exhaust fan speed can be modulated down and still provided the required exhaust, you will get not only fan energy savings, you'll get heating and or cooling savings. So again, this form is on our website. If anybody wants it, we can send it to you following the webinar. Other than that, yeah, I just want to remind folks one more time, you know, we're here for you. We don't expect you to be the experts on VFDs. We are connected to people who are even more expert than we are in VFDs. We have engineers on our staff who have domain expertise in different applications for VFDs. We have a lot of resource here, so we don't expect you to have to know every answer to every question. Please bring those to us, and we're happy to work with you and talk through your applications and hopefully increase your adoption of VFDs.
Awesome. Chuck, that was wonderful. I did add to the chat so everyone can see it, the hyperlink URL for this VFD info sheet, so that's accessible. I wanted to thank you, Chuck. Great session, full of chock-a-block content. Well done. And I wanted to just take this time to plug and promote one final session that's going to be happening a week from today, Tuesday at noon as well. We're going to have a session on HVAC controls, and Alex Rowe from Efficiency Vermont will be joining us to talk all about HVAC controls. So with that, thank you all for joining us today with this webinar. Have a great rest of your Tuesday, and hopefully we'll see you back here in 1 week time. Take care.